Hello, my dear, and welcome to our astronomy course. Today, we will continue studying our nearest star, Sun. And as usually, before we start a new big topic, let's see a video as usual. But in this is a reproduced variant, we will be not involved that video. Okay, so let's continue our lecture. You know, the solar magnetic fields extend high into the chromosphere and corona. I hope you remember all these two terms, chromosphere and corona. Yes. So it's a place where they produce beautiful and powerful phenomena. Study magnetic solar phenomena and notice 3 important points and 7 new terms. And first of all, it's the all solar activity is magnetic. The arched shapes of prominence are produced by magnetic fields, and filaments are prominences seen from above. And second, tremendous energy can be stored in arches of magnetic field. And when two arches encounter each other, a reconnection can release powerful eruptions called flares. Also, these eruptions occur from far from Earth, and they can affect us in dramatic ways. And coronal mass ejection, CMA's abbreviation, can trigger communications, blackout, and auroras. Third, in some regions of the solar surface, the magnetic field does not loop back. High energy gas from these coronal holes flows outward and produces much of the solar wind. You may have heard the common misconception that an auroral display in the night sky is caused by sunlight reflecting off the ice and snow at Earth's North Pole. It is fun to think of polar bears standing on sunlight slabs of the ice. But that doesn't cause auroras. You know that auroras are produced by gases in Earth's upper atmosphere, excited to glowing by energy from the solar wind. But what kind of activity would the sun have if it didn't rotate differently? And this is a really difficult question, because only one star is visible close up. But nevertheless, you can construct a scientific argument by thinking about the Babcock model. If the sun didn't rotate differentially, its equator traveling faster than its higher latitude. And then the magnetic field might not get wound up. And there might not be a solar cycle. Twisted tubes of magnetic field might not form and rise through the photosphere to produce prominences and flares. Also, convection might tangle the magnetic field and produce some activity. Is the magnetic activity that hits the chromosphere and corona driven by differential rotation or by convection? You know, it is hard to guess. But without differential rotation, the sun might not have a strong magnetic field and high temperature gas above its photosphere. And this is very speculative, but sometimes in the critical analysis of ideas, it helps to imagine a change in a single important factor and try to understand that might happen. For example, redraw the argument above. What do you think the sun would be like if it had no convection inside? How do you think? In that case, the sun is very bright. And the sun and its light and infrared radiation can burn your eyes. Every time, remember this. So you must take in great care in absorbing it. At sunset or sunrise, when it is safe to look at the sun, you see the sun's photosphere, the level in the sun from which visible photons most easily escape. Dark sunspots come and go on the sun, but only rarely are they large enough to be visible to the unaided eye. The solar atmosphere consists of 3 layers of hot, low-density gas: the photosphere, the chromosphere, and corona. 3 low-density layers: photosphere, chromosphere, and corona. Okay? The granulation of the photosphere is produced by convection currents of hot gas rising from below. Larger supergranules appear to be caused by larger convection currents deeper in the sun. The chromosphere is most easily visible during total solar eclipses, when it flashes into the view for a few seconds. It is a thin, hot layer of gas just above the photosphere, and its pink color is caused by the Balmer emission lines in its spectrum. Filtergrams of the chromosphere reveal spicules, flame-like structures extending upward into the lower corona. The corona is the sun's outermost atmospheric layer and can be imaged using a coronagraph. It is composed of a very low density, very hot gas extending many solar radii from the visible sun. Its high temperature, over 2 million kelvins, is believed to be maintained by the magnetic field extending up through the photosphere, the magnetic carpet, and by magnetic waves coming from below the photosphere. Parts of the corona give rise to the solar wind, a breeze of low-density ionized gas streaming away from the sun. Solar astronomers can study the motion, density, and temperature of gases inside the sun, analyzing the way the solar surface oscillates. Known as helioseismology, this field of study requires large amounts of data and extensive computer analysis. Nuclear reactors on Earth generate energy through nuclear fission, during which large nuclei, such as uranium, break into the smaller fragments. The sun generates its energy through nuclear fusion, during which hydrogen nuclei fuse to produce helium nuclei. Hydrogen fusion is the sun proceeds in three steps known as the proton-proton chain. The first step is the chain combines two hydrogen nuclei to produce a heavy hydrogen nucleus called deuterium. The second step forms high helium, and the third step combines the light helium nuclei to form normal helium. Energy is released as positrons, neutrons, gamma rays, and the rapid motion of particles flying away. Fusion can occur only at the center of the sun, because charged particles repel each other, and high temperatures are needed to give particles high enough velocities to penetrate this Coulomb barrier. High densities are needed to provide large number of reactions. Neutrinos escape from the sun's core at nearly the speed of light, carrying away about 2% of the energy, only 2%. Observations of fewer neutrinos than expected coming from the sun's core are now explained by the oscillation of neutrinos among three different types or flavors. The detection of solar neutrinos confirms the theory that the sun's energy comes from hydrogen fusion. Energy flows out of the sun's core as photons traveling through the radiative zone and closer to the surface at rising currents of hot gas, and sinking currents of cooler gas in the convective zone. Sunspots seem dark because they are slightly cooler than the rest of the photosphere. The average sunspot is about twice the size of the Earth. They appear for a month or so and then fade away. And the number of spots on the sun varies with an 11-year cycle. The result of this researching you may see on this slide, namely. Earlier, in a sunspot cycle, spots appear farther from the sun's equator, and later in the cycle they appear closer to the equator. This is shown in the Maunder butterfly diagram. Astronomers can use the Zeeman effect to measure magnetic fields on the sun. The average sunspot contains magnetic fields a few thousand times stronger than the Earth. This is part of the evidence that the sunspot cycle is produced by a solar magnetic cycle. The sunspot cycle does not repeat exactly each cycle, and the decades from 1645 to 1715, known as the Maunder minimum. You may see this on the diagram on the left part. Seem to have been a time when solar activity was very low and Earth's climate was slightly colder. Sunspots are the visible consequences of active regions where the sun's magnetic field is strong. Arches of magnetic field can produce sunspots where the field places through the atmosphere. The sun's magnetic field is produced by the dynamo effect operating at the base of the convection zone. Alternate sunspot cycles have reversed magnetic polarity, which has been explained by the Babcock model, in which the differential rotation of the sun winds up the magnetic field. Tangles in the field arch above the sun face and cause activity regions visible to your eyes as sunspot pairs. When the field becomes strongly tangled, it reorders itself into a simpler but reversed field, and the cycle starts over. Other stars are too far away for star spots to be visible, but spectroscopic observations reveal that many other stars have spots and magnetic fields that follow long-term cycles like our sun. Arches of magnetic field are visible as prominences in the chromosphere and corona. Seen from above in filtogram, prominences are visible as dark filaments, silhouetting against the bright chromosphere. Reconnection of magnetic fields can produce powerful flares, sudden eruption of X-ray, ultraviolet, and visible radiation, plus high-energy atomic particles. Flares are important because they can have dramatic effects on Earth, such as communications blackouts. The solar wind originates in regions on the solar surface called coronal holes, where the sun's magnetic field leads out into the space and does not loop back to the sun. Coronal mass ejection occurs when magnetic fields on the surface of the sun eject bursts of ionized gas that flow outward in the solar wind. Such bursts can produce auroras and other phenomena if they strike Earth. Science is based on measurement, but measurement in astronomy is very difficult. To discover the properties of stars. And astronomers must use their telescopes and spectrographs in ingenious way to solve the secret code of starlight. The result is a family portrait of the stars. And here you will find answers to 6 essential questions about stars. How far away the stars? How much energy do stars make? How hot are stars? How big are stars? How much matter do stars contain? And the last one, what is the typical star like? With this and the next lecture, you leave our sun behind and begin your study of the billions of stars that dot the sky. In a sense, the star is the basic building block of the universe. If you hope to understand what the universe is, what our sun is, what our earth is, and what we are, you must understand stars. Once you know how to find the basic properties of stars, you will be ready to trace the history of the stars from birth to death. A story that begins in the next lecture. Okay? And now let's start today's new lecture. Does your family include some characters? The family of stars is amazing diverse. In a photograph, stars differ only slightly in color and brightness. But you are going to discover that some are huge and some are tiny, some are astonishingly hot, and some are quite cool. Some are ponderously massive, and some are weeny little stars, hardly massive enough to shine. If your family is as diverse as the families of stars, you must have some peculiar relatives. Unfortunately, finding out what a star is quite difficult. When you look at a star, you look across a vast distance and see only a bright point of light. Just looking tells you almost nothing about the star's energy production, temperature, diameter, or mass. Rather than just look at stars, you must analyze starlight with great care. Starlight is a silent language of the sky, and it speaks volumes. Also, you want to learn such things as the temperature, size, and mass of stars, and you immediately meet a detour. To find out almost anything about a star, you must know how far away it is. A quick detour will provide you with a method of measuring the distances to stars. Distance is the most difficult measurement in astronomy, and astronomers have found a number of ways to estimate the distance to stars. Yet, each of those ways depends on a direct geometrical method that is much like the method surveyors used to measure the distance across a river they cannot cross. You can begin by reviewing this method and then apply it to stars. To measure the distance across a river, a team of surveyors begins by driving two stakes into the ground a known distance apart. The distance between the stakes is the baseline of the measurement. The surveyors then choose a landmark on the opposite side of the river, a tree perhaps, and thus establishing a large triangle marked by the two stakes and the tree. Using their surveying instruments, they sight the tree from the two ends of the baseline and measure the two angles of their side of the river. Let's see this figure, please. Now that they know two angles of this large triangle and the length of the side between the angles, the surveyors can find the distance across the river by simple trigonometry, as you do it at school. Okay? Another way to find the distance is to construct a scale drawing. For example, if the baseline is 50 meters and the angles are 66 and 71 degrees, you can draw a line 50 millimeters long to represent the baseline. Okay? Each millimeter on your drawing is worth 1 meter. Using a protractor, you can construct angles of 66 and 71 degrees at each end of the baseline. And then, as shown in this figure, extend the two sides until they meet at point C at our tree. Point C on your drawing is the location of the tree, right? And if you measure the height of your triangle, you will find it to be 64 millimeters, and thus conclude that the distance from the baseline to the tree is 64 meters, right? Modern surveyors use computers to solve these problems. But however you solve the problem, the point is that simple triangulation can reveal the distance across a river. To find the distance to a star, you must use a very long baseline, the diameter of Earth's orbit, for example. If you take a photograph of a nearby star and then wait 6 months, Earth will have moved halfway around its orbit. Are you agree with me? Okay. So you can then take another photograph to the star. And this second photograph is taken at a point in space 2 astronomical units, AU, from the point where the first photograph was taken. And thus, your baseline equals the diameter of Earth's orbit, or 2 astronomical units. And lines to the star outline a long distance sine triangle, as you can look to this figure. You then have 2 photographs of the same part of the sky taken from slightly different locations in space. When you examine the photographs, you will discover that the star is not in exactly the same place in the 2 photographs. This apparent shift in the position of the star is called parallax. The apparent change in the position of an object due to a change in the location of the observer. In this slide, you may see an everyday example. Your thumb, held at the arm length, appears to shift position against a distant background when you look with first one eye, and then with the other. In this case, the baseline is the distance between your eyes, and the parallax is the angle through which your thumb appears to move when you change eyes. The further away you hold your thumb, the smaller the parallax. Because the stars are so distant, their parallaxes are very, very small angles, usually expressed in seconds of arc. The quantity that astronomers call stellar parallax, P, is half the total shift of the star, as shown in this figure. Astronomers measure the parallax, and surveyors measure the angles at the ends of the baseline. But both measurements reveal the same thing: the shape of the triangle and thus the distance to the object in question. Measuring the parallax P is very difficult because it is such a small angle. The star nearest the Sun is one of our favorite stars, Alpha Centauri. It has a parallax of only 0.76 seconds of arc. And the more distant stars have even much smaller parallaxes. To see how small these angles are, hold a piece of paper edgewise at arm's length. The thickness of the paper covers an angle of about 30 arc seconds. You cannot use scale drawing to find the distances to stars because the angles are so small, and the distances are so large. Even for the nearest star, the triangle would have to be 300,000 times longer than it was wide. If the baseline in your drawing were 1 centimeter only, the triangle would have to be about 3 kilometers long. How do you like it? The blurring caused by Earth's atmosphere makes star images about 1 second of arc in diameter. And that makes it difficult to measure parallax from Earth's surface. Even when astronomers average together many observations, they cannot measure parallax with an uncertainty smaller than about 0.002 arc second. If you measure a parallax of 0.02 arc second in 10 times higher, the uncertainty is about 10%. 10% is about the largest uncertainty in a parallax measurement that astronomers can comfortably tolerate. So ground-based astronomers have not been able to measure the distance to stars farther distance than about 50 parsec. Since the first stellar parallax was measured in 1838, ground-based astronomers have been able to measure accurate parallaxes for only about 10,000 stars. In 1989, the European Space Agency launched the satellite Hipparcos to measure the stellar parallaxes from orbit above the blurring effects of Earth's atmosphere. The satellite observed for 4 years, and the data were reduced by high sophisticated software programs to produce 2 parallax catalogs in 1997. One catalog contains 120,000 stars with parallaxes 20 times more accurate than ground-based measurements. The other catalog contains over 1 million stars with parallaxes as accurate as ground-based parallaxes. The Hipparcos data have given astronomers new insights into the nature of stars. The European Space Agency plans to launch the GAIA mission in a few years. It will be able to measure the parallax of 1 billion stars to a 10%. NASA's planned space interferometry mission will be able to measure the distances of stars out of 25,000 parsec. Okay? For this moment, I think it's more than enough. Have you any questions or proposition? I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.